Alright, sorry guys, I have no idea what happened. That was weird. Okay, I think where I was ending off was talking about how rather than always use the distance from the sun to the planet, sometimes we'll use what's called an astronomical unit. Basically, the idea is that there is one astronomical unit between Earth and the sun. We've defined Earth to sun as being one. So therefore, Earth to Mars or Earth to Jupiter is now more than one because those are further distances, right? Whereas the sun to Mercury, the sun to Venus is less than one. It's an easy way to try to make numbers a little bit simpler. So, basically the idea then is if you want to try to find the k value was period squared over radius cubed. It's really easy then to work with years and astronomical units. Because how often does the Earth go around the sun? Well, 1 year. Right? And if you want to know the distance from the Earth to the sun, rather than knowing the actual value in meters or kilometers or miles, we'll just say, well, the Earth is 1 astronomical unit away from the sun. So it means the Earth has a k value of 1. Does that make sense? But the units for it are 1 year squared over astronomical units cubed. So we can use this then to help figure out data for other planets. This won't make sense until I just try an example. Okay? If you give me a funny look, let me just try an example. I promise you it's not hard. It seems more confusing than it is. Okay. So we can recognize using a telescope that it takes 60,190 days for Neptune to go around the sun. Okay. That would be easy data to collect. All you have to do is use your telescope and say, hey, look, there's Neptune, cool. And then 60,000 days later, you go, hey, cool, it's back. Does that make sense? So you managed to record that data. My question is then, well, how far is Neptune away from the sun? How do we figure out its distance from the sun? Okay. Well, we already know the k value for the sun. Remember, the k value for the sun was 1 year squared over 1 astronomical unit cubed. We know that because the Earth goes around every 1 year, right? And we know that the Earth is 1 astronomical unit away. Does that make sense? Well, that k value should be the same for the Earth because this is the data for the Earth, but it should also be the same for Neptune. So all I need to do now is throw in Neptune's values. Well, the only value I gave you for Neptune was that many days. Can we convert that many days into years? 164.9. Thank you. 164.9 years. But we're going to have to take that number and we're going to have to square it. Because that's what the formula calls for, right? You square the period and you divide by the radius cubed. The radius being what we don't know. How would we solve for the radius then if we know this is 1, this is 1, this is 164.9 squared, we still have to square it, and this one's r cubed. How would you get r cubed by itself? Well, I guess mathematically what you do is you'd take the r cubed, you'd times up to that side right there, right? And you'd take the 1 and you'd bring it down, you'd take the 1 and you'd bring it up. Which you wouldn't even bother doing, right? But maybe this helps explain why we chose to do it this way. Because what if we didn't use years here? What if we used days? Well, then this number would be 365, and you'd actually have to bring a number down to the bottom. Okay? And if we actually use the distance from the Earth to the Sun, like a big number, you'd have to bring it up top here. But if we just go with nice easy numbers like 1 and 1, then what you've actually made is a formula that says that the radius of Neptune cubed is equal to 164.9 squared. Can I visualize that? I lost you stuff. I'll do another example. We'll do a couple. So essentially for the Earth is 1 over 1, and then Neptune is going to be this over this. We're looking for the radius number. So all I need for you guys to do now, square this number and cube root it. Square 164.9 and cube root it. That'll get you your radius. $164.9 squared. You guys get 30 as well? Okay, 30 watts. Astronomical units. So basically the Earth to the Sun has a distance of 1 astronomical unit. Neptune is 30 times further away from the Sun than we are. That's all. Yeah. So its radius is 30 astronomical units. Or another way of being said is it's 30 times further away from the Sun than Earth is.
How many seconds?
Yeah, I guess in theory we should have had a few more based on this day's value right here. Honestly, I don't really want to worry about the sig dig's value right now. I just want to get the concept here. But yeah, we'd have to make that 30.070. Does that make sense a little bit for our first try at it? Once I've shown you a few of them, they all operate almost the exact same. If you go back to the chart, I really hope that that ends up being really close to what it said Neptune was going to be. So Neptune is 30 times further away. Okay. Let me try another example here. Okay. I hope after doing this twice, you guys will get the concept here. So Mars has 2 moons. I don't know if you guys were aware of this, but Mars actually has moons. We have 1, it has 2. Jupiter and Saturn have like 30. So here's one, I don't even know if that's it, right? Deimos and Phobos, I don't know. So what they're able to figure out here is that Phobos has an orbital radius of this and a period of this. And Deimos has a period of this. We want to find its radius. So here's how this would work. The K value for Mars is equal to a period squared over a radius cubed. The K value for Mars is equal to a period squared over a radius cubed of anything that orbits it. So do we know a value that orbits it? Well, yeah, we know all about Phobos. So Phobos, I can throw some values in. Its period is 0.3189 squared. What was that?
I don't know what Phobos was about. What did I miss?
I don't know, some planet that goes around Mars. And we know Phobos' radius, because it tells us its radius. Its orbital radius is 9378 cubed. You know how we did the sun example around the Earth last time? To make it easy, we just made the numbers 1 and 1. I don't have that option this time. That would get you the K value for Mars. But that K value based on Phobos' data should be equal to the data for Deimos. Okay. It should have the same values to it, right? Like the same constant. So for Deimos, the Deimos period is 1.262. We need to know its radius.
Can you use whatever units you want as long as you use the same?
Yes. That's one of the nice things about this is you just pick whatever units you want. Right? So when I'm done solving for the radius, since the other radius was in kilometers, this radius will be in kilometers. Right? The only rule would be that, like, you know how we had 0.3189 days? The other one better also be in days. So at this point here, it's just a bit of a math problem. How do you get this radius by itself? Well, we did this last time, right? To get the radius by itself, you have to times it up top there. Last time the numbers were 1 and 1, just to make it simple. This time we don't have quite as much luck. So you have to have like your radius cubed. Hopefully you guys can envision this then. This 9378 cubed number it's going to have to come up top and go over here. And this 3189 number, it's going to have to come down to the bottom. And then when you're done, you need to cube root the whole shebang.
No, not cube root. Put it to the power of root. Not that. If you know how to do it, you have to do that. Yeah. Do you know how to do it? Anyway. How do you cube root? No. I'm kidding. Okay, I'm like.
Anybody get that? Okay, in terms of units then, since these were both in days, you're good to go. So since the other one was in kilometers, this one's in kilometers. So this one rule, which is not on your formula sheet, just so you guys know, I'm not going to use it a whole bunch, in part because I don't know why it's not on your formula sheet. I mean, I'm supposed to teach you about Kepler's laws. This is Kepler's third law, and yet for some reason the government formula sheet doesn't put it on there. So I don't know. I feel like that's incongruent with each other. Basically, here's the idea. If you know the data for one planet, this is like planet 1, then you should be able to find the data for planet number 2 using this kind of formula here. You just need to know 3 out of the 4 pieces. If I tell you, how long it takes planet 1 to go around and how far it is, then if you know how long it takes planet 2 to go around, you should be able to find how far it is. Right? So it's honestly not that challenging. The only time you might get really stumped is if we use a planet around the sun, and it might not seem like they give you enough information because you know how long it takes the Earth to go around the sun, right? So you could have said, well, it takes 1 year for the Earth to go around the sun, or maybe 365 days. So sometimes the data might just be about Earth, and then you compare something else to Earth. Does that make sense? All right, 2 last examples, and we're done. Now I want to know what speed it's moving. Follow-up question. Speed is it moving? Well, we have that formula though. We're going to assume that it's more or less a circle still. We have a formula for that. Velocity centripetal is 2 pi r over t. As soon as I point that out, hopefully you guys will agree, this isn't actually a really hard question anymore at all. Because don't we have the radius now of that second moon? Yeah. Don't we have its period? Only one problem, the period was in days. And this number here was in kilometers. So minus a couple of conversions, it's really just plug some values in, right? So let's try it together. Is it? Yeah, because we're going to want it to be in meters per second by the time we're done. So, although when we use that K formula, you can probably use whatever units you want here. For this one here, we should go back to scientific ones. So your centripetal velocity would be 2 times pi times, this one here used to add a couple of zeros. So I'll make it 23462 times 10 to the 3. That'll take care of the kilometers issue. On the bottom, it was 1.262 days. Let's see. There are 24 hours in a day. There are 60 minutes in an hour, 60 seconds in a minute. Okay, I got 109,000 seconds. Anybody calculate that as well?
Yeah.
So there's my period, 109,000 seconds. So the formula for velocity is pretty easy. You just need to know your radius, which we now have, your period, which we originally had. It's just we got to do unit conversions. You guys kind of see why I made you do a lot of unit conversions in the first unit? Because it's going to come up. I kind of maybe did it more than I needed to in the first unit, but hopefully you're fairly comfortable in being able to convert between meters and kilometers and seconds and hours and when you need to miles and kilometers. Maybe yards and meters if you can teach you to do the right conversion ratio. Alright, 2 times pi times, let's see, 2,3,4,6,2.81,514 times 10⁻³ divided by n. You guys get something like this?
Yeah.
Yep. Cool. Alright, so it's traveling 1.35 times 10 to the 3 meters per second. Something like that. Sound good? Cool. I think I have one example left.
Yeah.
Cool. Let's get through that one and then you guys can have some time. Moon's orbital period and radius, 27.3 days and that many kilometers. You know, I know we've already done this at some point in our lives, calculate the mass of the Earth, but let's see whether we can use this data to confirm it. We're going to find the mass of the Earth. So this is actually not Kepler's laws again. We're just kind of going back to just in general gravitation stuff. So we have a period, we have a radius. How in the world are we going to get a mass out of this again? Because I mean, if we use the formula we just used, velocity is 2 pi r over t. I mean, I have r and t. Sure, that's awesome, right? But that doesn't give me mass. So this is, again, this is kind of like the last unit. One of your biggest struggles will be asking me, Chris, what formula do I use? Okay? And here, this is another example of, well, you have to kind of like put together your own formula. Why is the moon going around the Earth? Because of gravity. The force of gravity is why it's going around, and the force of gravity is equal to, well, it'll be because it's a centripetal force, because it's going around in a circle. So we can kind of make our own formula to relate these variables if we need to. We'll make the force of gravity be the centripetal force. Now, there's a couple of ways we can do force of gravity. Mass times gravity, like little m times gravity. That will get us the mass of the Earth, though, right? So we should use the big force of gravity, m1, m2 over r squared, because one of these masses is the mass of Earth. Oh, Fc. Well, Fc is really mass times acceleration centripetal. Now, we could do centripetal being v squared over r, mv squared over r. But I'm not going to pick that one this time. It's not wrong, it's just not helpful. Do we have the velocity? There's another formula for the acceleration. You guys remember the other acceleration formula? Let's use that one. Okay, let's take stock of where we're at again here. Why is the moon going around the Earth? Well, because of gravity. And it's going around in a circle, so your gravitational force is your only net force, and it's going in a circle. Here's the gravity formula. Here's the circular formula. We could have done mv squared over r. That's totally valid. It's just we don't have that information, because I don't happen to have a velocity, at least not right now. But I think I have all the rest of this, except for one thing. I don't actually have the mass of the moon. I don't need it though, do I? Because this is one of your masses, and that cancels the mass of the moon. Isn't that clever? So what's left? Capital G. Do we know that? Yep. M2, that's the mass of the Earth. That's the one we want. What's that? Oh, go ahead.
So the R is not cancelled?
You're right. We'll actually deal with that in a second. This radius right here is the radius around the moon, and we have that. Here's another radius. There's the period. Now, Emily, you pointed out the radiuses. They don't actually cancel, though. They combine. What ends up happening is if you solve for this mass right here, like the mass of the Earth, it'll be 4 pi squared r over t squared. This radius will come up to the top there, and now you'll have 3 of them. And the gravitational constant will go on the bottom. But now we've made a formula to calculate the mass of the Earth. All we have to do is know how far it is to the moon. And we just have to know how long it takes the moon to go around the Earth. And this will now tell us the mass of the Earth. So here's hoping we get the 5-point number that we're hoping we get, right? So one more thing I need to point out, guys. If I tell you that you have an orbital period and radius, don't have to add the radius of the Earth in there as well. Okay? If I just tell you the distance from the Earth to the moon, then you have to add the radius of the Earth itself. But if I'm very specific and I call it an orbital period and an orbital radius, you're good to go. You don't have to add anything extra. So, the only thing we have to do is convert them. Because this is days and kilometers again, so we don't have the right units. 27.3 days times by 24 hours in a day times by 60 times by 60. Alright, so that's how many seconds it takes for the moon to go around the Earth. And then you also need to know the kilometers. I think for this one here, I'm just going to add 3 more zeros when I'm done though. So it's 4 times pi squared times 384,000,000. Cube that number. Divide by 6.67 times 10 to the minus 11. And then your period, I'll just draw an arrow here. That number gets. One more thought. As you guys are frantically typing things in. Remember Kepler's law? The third one was that you had a period squared and a radius cubed. Period is squared, radius is cubed. Everything else, by the way, is a constant. 4 and pi squared is a constant, and g is kind of a constant. So in a way, this kind of is a little bit like Kepler's law. I know it's upside down, but it does have radius cubes, period squareds. Anyways, let's get an answer and then we can be done for the day. So this took a little longer than I was hoping. 384,000, then add 3 more zeros to put it into meters and cube that. And then divide by 6.67 times 10 to the negative 11 multiplied by 2358720. That's the number. 2385720. And that one gets squared. You guys get this? Okay. That's not the value that we have on our data sheet, but it's kind of in the ballpark, right? Isn't it one on the data sheet 5.97 to the 24? This is 6.02 to the 24. It's not bad. It's close. Why is it off? Why is it not? Why is that slightly off from what we consider to be considered right? Yeah, we were assuming it was a perfect circle, but we know now, according to Kepler's laws, that it's slightly elliptical. So, I mean, it's close, but the moon actually goes around the Earth a little bit further on one side, so it actually is slower on one side than the other. So, and this is pretty close, but it's as good as we've got. Okay. You guys have any questions? Okay, quick summary of the day then. The last thing I need you to be able to do is make like an FC equals an FG for planetary data. And I need you to know Kepler's 3 laws. 2 of the laws really require nothing special. The third law has a little bit of math to it, the t squared over radius cubed kind of formula stuff. I won't test you on that a whole lot. Good, okay. You guys have questions? Alright, okay, I can give you about half an hour more time to study for your social test or start working on your assignment. So, Monday, We're gonna do a lab Tuesday, Wednesday are work days, and Thursday we're gonna try quiz. Okay? Okay.